So which is the main goal of my work? In particular, in time series analysis, we are often interested in learning the true covariance matrix, C, which governs the underlying stochastic processes. The problem is that this matrix is unknown, and in real-life application, we can obtain only one historic data set to which compute an estimation of this true covariance matrix C, which is the empirical estimation E. So, in particular, we are looking for an optimal estimation of the true covariance C and of its inverse, the precision matrix J, which has to be robust to high-dimensional noise. Again, in particular, having access to only a single empirical realization E. During this work, I will explain the construction of the estimation of the true covariance matrix C in both the high information and low information regime, the so-called course of dimensionality regime. A real-world application for where we need the knowledge of the true covariance matrix or a clean estimation is, for example, the portfolio optimization. In particular, as we can see in this formula, by the Markowitz theory, to compute the weights vector value of our portfolio asset, we need to know the clean estimation of the covariance matrix sigma. In particular, for the numerical experimental part, I will work with the 400 most liquid stocks of the Standard & Poor market over the last 20 years here. What about the related works? My work is the most inspired by two papers of the Buchholz group. In particular, the first one is the work of Ban in 2016, which has been recently extended by España in 2024. Again, I remember that these two guys are working with Jean-Philippe Bouchot, one of the most important econophysics in the world. I will introduce the 6 methodologies that I've tested and compared to make an estimation of the covariant matrix. In particular, the first one, the most simple, is the sample covariance matrix. I will not discuss, but I will focus on more sophisticated techniques. In particular, let's introduce 2 estimators based on the random matrix theory. So we have to make an assumption. We are working with rotational invariant ensemble, which means that there are not preferred direction for eigenvalue spaces. This is a very strong assumption, but it's very useful by a practical point of view, because I remember that we are working with a single realization of the empirical covariance matrix. So from this, we compute both the eigenvalues lambda and the eigenvectors u, and then we will clean in some ways this matrix. The random matrix theories give us some theoretical result to analyze the probability distribution of the empirical covariance matrix given the knowledge of the true covariance one. On the other hand, we are focusing on the opposite problem. So we would like to reconstruct a probability distribution for the true but unknown covariance matrix given a single realization of the empirical one. So in this case, there are two possibilities. The simple case is the isotropic one, when we are assuming that the true covariance matrix is the identity. So basically, we are not consider an interaction between our variables, and this leads to the Marchenko-Pastor distribution, which is one of the most important analytical results of random matrix theory. On the other hand, in a more generic case, we will introduce the rotational invariant estimators, which were proposed by the Buchholz group. So the first one is the eigenvalues clipping, which is basically based on the Marchenko-Pastor hypothesis. As we can see in the formula, the clean covariance matrix is basically a spectral decomposition on the eigenvectors samples on the samples eigenvector, where we just adjust the sample eigenvalues. In particular, we consider as the null hypothesis the Marchenko-Pastor distribution. I remember that is the case we are assuming that the true covariance matrix is the identity. And in this case, if the eigenvalues are inside the bulk, which means that they are basically noise, we just shrink to a constant, we just shrink all them to a constant. On the other hand, if the eigenvalues is outside the bulk, which means that this is a really meaningful eigenvalue, then we keep it as it is. So this is the first method based on the random matrix. The second one is the one proposed by Buchholz, when the main idea is not assuming the true covariance matrix as the identity, so we are considering the most general case. And the idea is that we are trying to numerically invert the green function of the eigenvalues distribution. Another method proposed by the Buchholz groups was basically the inverse Wishart regularization, which is systematic error correction, especially in the case of working with small number dimension n. Then this method was proposed by another student of Buchholz, which is the Kendall correlation, and the idea is to obtain an estimation of the covariance matrix by mapping the Pearson linear correlation coefficient with the Kendall one, defined in the formula, which is basically Pearson correlation coefficient between the sign of the difference of the rank of our time series. We have to observe that among all these methodologies, this one is the most computationally intensive. Then we totally change our framework. We moved to the informational filtering networks, which is one of the most important research topic of the head of this group, Professor Russell. In particular, I used the TMFG construction. The main idea of informational filtering networks is to make a network with starting from a raw dataset, and then make some filtering to all the possible connection to keep only the most relevant connection. In particular, I use the TMFG, which is a network construction using tetrahedron. One of the most important advantages of the informational filtering networks is the log-on decomposition. I mean, if all the other methodologies were based on the idea that obtain most clear possible covariance matrix and then invert it numerically because we need the precision matrix for the Markowitz formula. The Hasses-Isea is directly focusing on to obtain a sparse and more noise robust estimation of the precision matrix J. This is possible through the logo decomposition, which allows us to rewrite the joint PDF as local contribution of both click and separators. So in the end, for each of the previous methodologies, I implemented a shrinkage version, which is a convex combination of the cleaned estimation and a target matrix, where I implemented two different typologies of target. The identity one for independent but almost elastic noise, and a diagonal matrix where the entries are the standard deviation, which is target from heterostochastic noise. So let's describe my numerical experiment. In particular, I implemented rolling window training experiment. So working with the 400 most liquid stocks of the Standard & Poor's, and the data were daily returns over the last 20 years. In particular, for this point, I fixed the training number of observation to 800, then both the validation and test observation to 16. The main idea is that until we have data in our time series to use the training part to compute the clean estimation of the covariance matrix with all the previous methodologies, and use them to compute the Markowitz vector W. Then move to the validation part to choose the best shrinker parameter, and then move to the test one to compute the out of sample performance, which are the very important performance of our experiment. Then update all, then just move all this time block to a parameter rolling and repeat until we have data to use. So in this slide, there is the box plot of all the possible methodologies, where the parameter Q, that is the number of variables over the number of observation, is fixed at 1/2. So basically, we are working with the twice number of observation with respect to the number of variables. And in this the information regimes, more or less, the results are basically the same. In particular, the first 6 are the basic estimation, while all the others are the shrinked version. But again, the results are more or less the same in these regimes. That's the reason why we choose to repeat the experiment, varying the parameter Q, which I remember is the number of observation over the number of variables over the number of observation. And then we can see that for the basic methods, they split into 2 groups. The first one are sample and the 2 methods proposed by Bouchot's groups, which are the methods most affected by the low information regimes, the course of dimensionality. On the other hand, we can see the methods based on the Marchenko-Pastur, the Kendall correlation, and the TMFG, thus are much more robust to low information, to noise. That's a very interesting thing, I think. Then the same plot with both the shrinkage, and we can see that again shrinkage is mandatory to avoid the loss information of the course of dimensionality regime. So which are the open challenges of this work? First of all, I would like to extend the experiment to other markets. In particular, I would like to test on the Japanese and European market. Then I would like to extend to other strategies. I remember that for the formula of the portfolio weight construction of Markowitz, there is this vector G that in the previous case was the it was a vector by ones, the minimum variance strategies. I would like to implement 3 other different choices for the G vector, which are the omniscient case, the mean reversion, and the random long short, to be consistent with the Bushow's group supports. So that's all. Thank you for your attention. Yes, in a first part, just to let me share that all my numerical code was done in the right way. But talking with my supervisor, he said that it's much more impactful working with a real data set with respect to the synthetic one. Yeah. Yeah, see, with the one standard deviation, yes. Because in the all the theoretical background of random metrics, they always say to work in the regime where the Q value is less than 1. They always work with more information with respect to the number of variables. On the other hand, so that's the reason why the performance of the pure random matrix model of Bushow doesn't work in that regime. In their works, they especially said that they are working with the Q parameter fixed to 1/2. One of our original contribution is to explore all the other regime. Yeah, it's the Q is smaller than 1. When Q has the random matrix for factor. Where Q is smaller than 1, then clipping in this picture, I don't remember, but again, by previous plot that I've made, when the number Q, when the value Q is less than 1, except to the sample 1, which is starting to increase, more or less the performance of the all other methods are the same. Thank you.